The broadcast is now starting. All attendees are in listen-only mode.
Welcome, everyone, to today's webinar, Vision Systems for Deep Learning, presented by Basler AG and hosted by Photonics Media. My name is Robin Riley, and I'm the Photonics Media web editor. I would like to introduce Mr. Felix Chemnitz, Product Market Manager responsible for the Basler product portfolio in the medical and life sciences markets. Felix will be speaking today on different types of vision systems that can be used to deploy a trained neural network in the medical and life sciences fields. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. We encourage you to ask questions throughout Felix's presentation. Type your question in the question box to the right of your screen, and we will answer as many as possible at the close of the webinar. And now, with nothing further, I would like to introduce our speaker, Mr. Felix Chemnitz. Welcome, Felix.
Welcome. Thank you, Robin, for this great introduction, and looking forward to give a webinar about this vision systems for deep learning. So I will start right away. My name is Felix Chemnitz, and as Robin said, I'm the product market manager for the medical field or the medical portfolio of the Basler AG. This is why my presentation has in general a validity for all vision systems, but the examples come more or less all from the medical field. To give you a brief overview about the agenda of today's webinar, I will start with a short overview about the Basler AG, so you know who is talking to you and what's my background or the background of the Basler AG. Then a little bit of the motivation, rise of deep learning. Why is deep learning in our daily life so important or becoming that important? And after that, we will directly jump into the three different types of vision systems, which are embedded-based, PC-based, and frame grabber-based. And after that, we will have time for a question and answer session where you have the ability to raise your questions. Good, then we will start with the first point, the Basler AG. The Basler AG is a global company located with its headquarters in the northern part of Germany, which you can see here, which is Ahrensburg. And the company was founded in 1988 by Mr. Basler, who is still the chairman of the supervisory board. And we started to grow bigger and bigger. And I just wanted to give you an overview about the different locations where we are located. Interesting is that we have a big pile of branches in Asia with the second production line in Singapore. So the main production line where all of the cameras for the EMEA and US region come from is directly in the headquarters in Ahrensburg, and the second production line, as I said, in Singapore. We will have a subsidiary also in Exton in the US, or we have one. To give you a brief outline how big we are around 800 employees at the moment, doing 150 million revenue in 2018. This means in numbers, we sold around 400,000 cameras in 2018. To show you the regional revenue split, and this makes it clear why we have such a strong number or such a great number of subsidiaries in Asia. This is why we did this because we are doing 45% of our revenue directly in Asia, 29% in EMEA, and 26% in the US. What I wanted to mention here also is that we bought a company called Silicon Software in 2018. This will become interesting while I'm talking because this company is producing frame grabbers as well as software for these frame grabbers, which makes it available for the neural networks itself. To give you a further overview about our product lines, we have different cameras. So here you can see the area scan cameras as well as line scan cameras with different interfaces for the factory automation business to inspect, let's say, for example, the production of mobile phones. We have a portfolio dedicated for the medical and life science field, where we have a separated production line, which is ISO 13485 certified. And these cameras come along with additional firmware features to be explicit suitable for the medical and life science field. As well, there's a 3D camera in our portfolio, which gives you the ability to not only have a two-dimensional view, here you have the three-dimensional view with the depth information as well. Then we have core biz for these cameras and a module business for development and evaluation kits, as well as the small cameras called the DART series, which work together with these evaluation kits or development kits for embedded hardware, where you can directly connect those small cameras or small camera modules. For all of our cameras, we provide you with the components such as cables, lenses, which are directly tested at Basler, produced under our requirements, and so we can ensure that all of our cameras work with the components supplied by Basler perfectly. We have another point, which is the lighting SLP. So to say it in easy words, this controller or the smart lighting gives you the ability that the camera can control the lighting itself throughout our SDK, which gives you the ability to connect easily each kind of LED lighting to this controller and control it via the software development kit of the camera itself. And here on this lower part, you can see the silicon software frame grabbers, where I will jump in a little bit later to show you how you can use this for a frame grabber based embedded vision system. This slide should give you an overview about the entire process chain of a vision system. So we start at the image acquisition with the camera modules, light, and everything you need. Then it goes to the image transmission. So this means the interface cards, cables, hubs, and the software itself. And then you have the image pre-processing, which runs on the PC side in parts directly on the camera, on the FPGA, as well as on the frame grabber when you use a frame grabber based system. Then we have here the image analysis, which means really deep learning or software for embedded solutions. And this leads to this consultancy field where we can give you guidance how to set up the board design itself for an embedded system, including the software which should run on this embedded board for your system. Tailor-made solutions is now the last point about the Basler AG. This means we have a real custom project teams, which gives you the ability, if you say, oh, this camera doesn't suit my space constraints, everything in that direction, I don't like the color, this blue, which they thought would be the best for the medical market, is not what I want to use in my system. We have the ability with the custom projects team to change nearly everything inside and outside the camera, depends on your wishes. And yeah, we would be glad to talk with you or our custom projects department about your needs for that camera stuff. To come to the next point, the rise of deep learning, I have prepared some slides to give you a brief overview what we think about deep learning and how we see the market. So as the umbrella term for AI, we see this artificial intelligence, and this covers the machine learning, the deep learning, and in these times the convolutional or the neural networks. And in this webinar, I will use the term most of the time artificial intelligence to represent the whole field of AI. So artificial intelligence and the rise of deep learning. These algorithms, as you will know, are in the market or are developed far long time ago, but there was not enough computing power to really expand this field or to make it usable. So by now we will transfer this into the artificial neural networks, and this will give you the ability to enable new applications. I will talk a little bit about this in a second, and improving, for example, fields or applications from the factory automation business, which we see in inspection business, or in, more or less inspection business, let's say it like that. So, vision systems for AI, difference between classical machine learning and the real image processing. So the classical approach, as you will see here, we have an image of a steel belt, and in former times, the designer or the developer was able to handcraft image features. So they took 2, 3, 4 images. Oh, this is a mistake. There's a hole inside this steel belt, and they could decide what rule they want to apply to this image. So in that case, you had the acquisition of the image. You did a binarization to get it really clear between white and black. And then you thought about, okay, what's my measure to see if it's a defect or not? And we choose the distance. So if this maximal distance in the hole is bigger than, let's say, 1 centimeter, we would say, okay, it's a defect or it's no defect. So this was easy and could be rolled out through the CPU or through the FPGA. But you need to decide and understand the rules why you choose this as a defect or no defect really in depth. By now, with the machine learning approach, you have the ability to do an automatic feature design by the network. And this is a little bit tricky because the developer does not understand fully or does not understand how to separate the classes, and there will be a black box decision within the network. So you feed in the network with a tremendous amount of images, which you have labeled as, oh, there's a defect or there's no defect, and the system itself will learn to make decision rules or create decision rules why this is a defect or not. We will not understand this. But after you have trained your artificial neural network, you will have this inference, this trained neural network, and you can put in the acquisition image, and the network itself will decide if it's a defect or no defect. Good. Just to make clear the difference between the classical approach, where you needed to understand the rules fully. Here you don't understand the rules, but it gives you the ability to flag images and create the decision rules by itself. The fields we see AI in is, for once, the microscopy field, for example, in the medical field, where we have those cell segmentation, classification, or even counting of the cells automatically. Or in pathology, if you think about whole slide scanning, where you will have to define these diseased areas or the diseased tissue. And these networks give the pathologist the ability to don't have to screen the whole slide, only to see or have a look at specialized or the segmented areas where the network says, okay, in this cell, this is probably a diseased kind of tissue. The other big field we see is the ophthalmology part, where you have this retinal images or the OCT images, and there you have, for example, the blood vessel segmentation, the fluid segmentation, or, for example, detection of diabetic retinopathy. But these are only examples. You can think about lots more of application fields such as magnetic resonance imaging, ultrasound imaging, electrocardiogram, interpretation. All that can be learned by vision or by AI. We see different other fields from the factory automation. We call this in Basler language. So there could be food inspection, where you have to differentiate oranges from pineapples from whatever. You will have a pattern recognition, surface inspection. We see stuff in the traffic field for example, a car classification or railway inspection. In the classical factory automation, here we have as well a steel belt. There you can have this, what I explained in 2 slides before, a defect classification or an assembly verification while putting together, for example, a mobile phone. Or in retail, you can have this object detection, this kind of liquor at the right spot, or the cigarettes at the right spot in the kiosk, or you can have a face recognition for entrance, admittance. All that stuff could be learned by AI. So to move on, an example directly from the medical field. Özcan Aydogan, he did a paper about this, and to give you a short explanation, they trained a network using tissue from a biopsy under the DAPI image. So this would be a fluorescence image. And if you put on the blue light, you will see this autofluorescence of the tissue. So this is the first image. And then you have to stain the image and do a H&E staining with different chemicals to make the inside of the cells and the tissue itself visible. And so in this case, they showed the artificial intelligence, or the CNN, the image, which was the fluorescence image, and afterwards they showed the stained image. And by now the network learned to transfer this DAPI image or this fluorescence image into this virtually stained image. And if you have a look at it, it looks a little bit different, but the results are so good that a pathologist can use this virtually stained image to do his diagnosis. So what this means, from the not stained tissue to the H&E stained tissue, it would take about 45 minutes of work for a biologist or chemist to do the staining. And within now, you have the ability to use a neural network to show them this image, which you can get instantly from the biopsy or from the tissue from the biopsy, and have seconds later this virtually stained image. So this is an example how a trained neural network can influence the type of working within these times. Good. So this was the motivation why we have a look at artificial intelligence. And now I will move over to the vision systems and show you how we will or how we see the inference vision systems. So in our termination, it says that we have on the one side the camera itself. Then you have this interface where you can see, we showed here GigE, USB 3, MIPI CSI2, to transfer the data directly from the camera to a kind of inference host, where the trained neural network is running and will give you the ability to run your trained neural network. This is clustered, the image acquisition or the image processing pipeline, into 4 steps. And in this webinar, we will have a look at the first 3 steps. So this means the image acquisition, where we grab the image directly from the camera. And this means in this step, you will tune the camera, set the exposure time, set the region of interest, think about, do I use a trigger, a software trigger, hardware trigger, stuff like that. After that, the image will be pre-processed. This differs a little bit on which kind of camera you choose. If the camera has the ability to have the pre-processing within the camera, this means if you have a color image, you would have a deburring to get from this raw image data to this color image data, or you will have the ability to do a sharpness enhancement to get straighter outlines or more crisp image. And you will have the ability to cut the whole image down into smaller pieces which can be fed into the inference of the deep learning system. So to cut the image down. And then the third step is to run this inference on these small parts of the image, which gives you confidence that, for example, in my example, this is a good cell, this also, but here's a confidence of 98% that the pathologist should have a look at this part of the image to see if there are diseased tissue in this part of the image. And after that, this will result in a result visualization, but this is not part of the vision system itself. This would be your part if you create a vision system, how you want to present this to the end user. So this is not part of the presentation. We will now have a look into 3 different vision systems for artificial intelligence. So this means we will have a look at an embedded inference system, a PC-based inference system, and a frame grabber-based inference system. And we will compare these 3 by integration effort, performance of the system itself, and the total costs of ownership, which you have to calculate for such a system. And the assumption for this comparison is that you have a trained inference, which you did with, let's say, TensorFlow. You set up the system or the network, you trained it, and you have a ready trained inference, which you can deploy to your kind of embedded or kind of inference system you want to choose. Good. So we will start with the embedded system for inference. Because I'm from Basler, I took our cameras as the example. So we will start on the left side with the camera itself as the device which takes the image. Then you see here in the middle the interface, and on the right side we have this inference host. So I will start on the left side with the Dart MIPI, which is called like that. The Dart family is one of our small camera families, which has a 29 by 29 outline. And the connection is MIPI, which comes from the smartphone industry and gives you the ability to connect the camera to an inference host or a processing board by this FlatFlex cable. So the camera comes around with the sensor. I will not go into that into detail because I think your requirements will differ totally. Each and everybody will have different requirements for their sensor and the resolution, if it's a global shutter, rolling shutter. So we have different models of these. If you want to go deeper into detail and choose the right camera, we will be glad to consult you on this and give you guidance which camera would be the best for your system. Interesting regarding this camera is that it has an ISP, which stands for image signal processing, directly on the camera. So with this camera, you are able to pre-process the image. So the image data is grabbed in RAW, and you will pre-process it in the image signal processing pipeline, and it will transfer via the MIPI CSI2 interface to the, in this case, an NXP IMX8 board, the data or the pre-processed image, which means if you have, as I said, the color image, it will do the deburring directly on the camera. It will do sharpness enhancement if you want, and different other image enhancement algorithms are directly available on the camera side. After you transferred the image via the MIPI CSI2 interface, it will be processed by the digital signal processor and then fed into, let's say, into the GPU or the CPU. And what I mean with this Pylon 6 directly on top here, that our SDK for the cameras is available for Linux, Windows, and in this case, this is an ARM-based processing unit from NXP, and we also provide a Pylon 6 with the Linux for ARM-based software. So you can directly run our drivers on this board and on this Linux machine or system. So this gives you the ability to control the camera directly from this interface and grab the image data. So this board comes along with a GPU and a CPU. So then you can choose, I marked in here TensorFlow. You are free to choose your framework as you want and to deploy your ready inference to this board. This is a little bit tricky. We set up to do a kind of proof of concept. One of our students set up this vision system where we trained a network. So we used a TensorFlow network with 11 layers. So this means we had 4 convolutional layers, 2 max pooling layers, 1 to flatten this, and I think 2 dropout layers and 2 fully connected dense layers at the end. And this system is able to decide between 5 classes of little Lego people, which kind of Lego people this is. So this can decide if it's a chef, it's a prisoner, if it's a policeman, a fireman. And we can do this with an accuracy of 99.2%. And used for this 200 images of each class of each class, of 200 of prisoner, 200 of a chef. And for this, it took about, I would say, 4 days for them or for the student to set this up and to take this 1,000 pictures and make it available to the system. We trained this system on a GPU, which took about, I would say, 15 to 20 minutes, and then deployed it to the embedded board itself. In this case, we took a Qualcomm 820 Snapdragon and let it run only on the CPU, because with an embedded system, it's kind of critical to, or it's a little bit tricky to deploy ready inference so that the system uses also the GPU to calculate or to run the inference. This is why we wanted to show you that this is a real, not the biggest net, but 4 convolutional layers are already a requirement for such a board. And it takes only 5 seconds for the board to run through the inference and give with a probability or confidence of 99% out what kind of class it detected below the camera. Here's an image of the setup itself. So here on top, we have this MIPI camera with a small S-mount lens. And in this frame, you should put the Lego people, which should be detected, connected via this flat flex cable I was talking about, and then connected to the Qualcomm board, which gives out the confidence and the map or the picture what it detected. So this is one example how an embedded system or an embedded vision system for the inference could look like. And now we will have a little recap. So we start with the Basler Dart, for example, MIPI CSI2 connection and a processing board. And these are complex structures. So we have the ability to use evaluation boards, but these are not really plug and play. With the Pylon, you have the ability to connect the camera and grab the first images easily, but this is with an evaluation board. And for the ease of integration, it took us, as the manufacturer of the camera, some time to get it running with this board. So we would say the ease of integration is not that good, so only 1+. The performance is also not that high. It depends a little bit on how you write your code and if you will make use of the GPU in this system. And these ones can, of course, be boosted by using special chipsets for AI. So, for example, the Intel Movidios could be placed on a board, but ease of integration also means that you will require special hardware for this system, and you won't use this board or this evaluation board in your final system. This is only for testing or proof of concept. So you will have own board design later on, and this will take some time and need some special requirements, or you need to have the know-how how to set up such a board, how to implement those chips, and this makes it a little bit tricky. For the total cost of ownership, this is, I think, the cheapest system you can build up, because such a vision module or dart camera would be, let's say, around $100. And the processing board itself, for an evaluation board, you would pay between $200 and, let's say, $400. But if you go down to an own board design, a real custom board design, you can go much cheaper in the processing board itself. This would be, I think, from my perspective, an interesting point if you think about point of care applications where you build a device directly meant to be used on the patient side. This would be the most interesting setup or the cheapest setup for your needs. Good. Then we will move on to the second vision system for AI, which would be the PC-based system. And in this case, we have also the ability to take Basler cameras. These are a little bit bigger and housed, and they come around with a GigE and a USB or USB 3 interface, which are standardized in the GigE vision or USB 3 vision. And on the inference side, you will have this industrial PC, which gives you the ability to take components, I would say, directly off the shelf. And as well, we have for this kind of machines with Windows, Linux, or Mac OS, we have the ability to provide you with the SDK, with the Pylon 6 SDK, which can control the cameras directly via the GigE or the USB. We have around more than 400 models of these cameras, so this is why I also won't talk about the sensor requirements for these systems. If you see we have 400 models, you have the ability to choose between more or less each and every resolution. So this would mean you have from VGA resolution up to a 20 megapixel resolution, each in this field, and you must choose, or with our consultancy, we are keen to help you by choosing the camera, choose the right resolution and the right type of sensor for this system. The camera has a FPGA, field programmable gate array, inside the camera, which makes it able to do the pre-processing, as we saw, one of the 4 steps which are needed to have the image acquisition pipeline. And also these cameras come around with the deburring, with the image enhancement, like the Basler PGI, which gives you a couple of abilities to improve the image itself. And then you can transfer this plug and play via the GigE or the USB. And then you can make use of the GPU in the PC. You can do it on the CPU, but this won't be the best performance which can be given. So I think GPU would be the best way. And I draw it in here. For example, you can use OpenCV, or if you want a commercial product, it would, one of the opportunities would be to use Halcon from the MVTech company, which has already the ability to do some artificial intelligence tasks or neural network tasks, and the software comes along directly with the capability to do this. This also has a hardware acceleration where you can make use of the GPU directly from this host software. In the OpenCV case, it's for free. And in open source software, in the Halcon, it's a commercial product and you need to buy it, for example. So to make this round, from our perspective, the PC-based system is the most easy one to use. That's why it's got 3 pluses at the ease of integration, because you can just grab a camera, connect it via USB 3. It will be detected by the PC itself. You install the pylon, say grab image, and then you go. As well as you buy software directly from the shelf. You buy your Halcon, say, okay, that's my artificial intelligence or my neural network task, and you will be able to set this up real quick and easy. But the performance is a 2+, because it depends on the PC system you're using. And from our perspective, you need to ensure that you have a GPU. Mostly in this case, NVIDIA GPUs are used because this is the most prominent for artificial intelligence, or the usage in artificial intelligence. And to get a real high performance system, there is the likelihood that you need to have more than one GPU in the system, and this will increase your total cost of ownership a lot. So you have the ability to buy a standard NVIDIA graphic card or graphical processing unit for, let's say, around 200 euros, but this is not the industrial grade. This is the end user type of graphic card. And I think they will increase in price a lot if you want to have a long-term availability, or you want to go up into a Quadro RTX 8000, which would be, I would say, around 5,000 euros for a GPU. And even if you want to go higher in performance, you need to combine 2 or 3 of that, and this can lead to system costs of $15,000 to $20,000 easily to get a real high-end performance system for your artificial intelligence. Good. So I think this was the overview about the PC system itself. And so we will quickly move on to the frame grabber based vision systems. And in this case, there's also availability of Basler cameras for this kind of system. So this would be a camera with the camera link interface, or with the new Coax Express interface, so CXP12, which gives you the ability to get a tremendous amount of data through this interface. And also these cameras come around with a whole bunch of sensors, mono or even color if you want, and all of them have the FPGA on board. So this also gives you the ability to do the pre-processing on the camera. And then for this kind of interfaces, for the camera link as well as the Coax Express, you need an industrial PC combined with a frame grabber. So this is a card which will be inside this industrial PC connected via PCI Express, and gives you the ability to connect these cameras to the frame grabber. But to get this running, you have a big FPGA, as I said, the brain of the camera to do the deburring and the pre-processing of the images. You have a big FPGA as well on the frame grabber. And this gives you the ability with the frame grabbers from Silicon Software that you have a software developed by Silicon Software, which is called Visual Applets, which will control the frame grabber directly from the industrial PC side, and gives you the ability to do the triggering of the camera, set the exposure time, and do all the requirements, all the specs of the camera you want to set to the camera. And Silicon Software as well developed a CNN-ready kind of block, which gives you the ability to deploy your inference of your trained neural network directly to the FPGA of the frame grabber. And with this, from our perspective, you will have the most powerful and robust system for a high throughput application. And I have some examples for this. So Silicon Software made a demo where they used a surface inspection of steel On this roll, there are printed images like this ones from the 6 classes. So rolled in scale, patches, maybe some crazings on the stuff, pitted surfaces, inclusions or directly scratches you can see here are on this roll. And here on the top, you can see the camera, which takes, it's connected via camera link interface to the frame grabber and takes the images of this roll you can see spinning here in this animation. And this gives you the ability to do this image acquisition, image classification, and the probability or the confidence in which direction this, or in which class this image is classified, and the confidence. And what's really interesting and makes it so feasible to use a frame grabber or an FPGA with a frame grabber with a big FPGA. So here Silicon Software compared the Kintex 7, which is the FPGA on this frame grabber, the Marathon VZL, and NVIDIA GTX 1080, which is a high-end GPU. And as you can see here, you have the ability to get this frame grabber a long-term availability, which is, of course, in the medical field, a big benefit, because as my background from the medical field, we always deal with certification issues. And if you need to change your GPU, for example, in a system after maybe 3 years, or let's say you designed in it at the hype of its life cycle, you will get it for maybe 1.5 or 2 years. After that, you need to take a new one for a new product. You need to go through recertification in this medical field, and this would lead to a lack of products in your portfolio. So it's easier to go with the frame grabber, which is available for more than 15 years in the market. And what's really important and what I wanted to point out in this slide is that high-end GPU is able to perform 1063 inferences per second. So 1063 of these images are processed in this inference, but the frame grabber gives you the ability to provide you with 7,812 inferences per second. So this means you have 7.3 times higher performance than you have with the GPU. And this makes it in high throughput applications so feasible or so interesting to use a frame grabber for this kind of inference systems. Good. To sum that up, here's a little graphic. So you start with the frame grabber, the image acquisition from the camera, you have the image enhancement, the pre-processing, and all these blocks are made in visual applets and gives you the ability to put in your specifications you want to have. And here I highlighted the ability to put in this CNN ready block where you can deploy your trained inference from a TensorFlow or other topologies from different frameworks you have already done. So, and this makes it so easy. In case you won't use this visual applets as well as the CNN ready building block, it's quite a challenge to deploy inference to an FPGA, and you have to have deep FPGA knowledge, which is not given to everybody, and it's also, yeah, it's hard to learn. And so this makes it quite easy and easy to use this FPGA together with an inference. To get to nearly my last slide, to compare all these vision systems for AI, we started with the embedded system for AI, which is kind of hard to integrate because you need to know what you're doing to get your own board design if you don't want to use the evaluation board itself, and you may need to make sure you're able to design a board, get it running with the Linux, then include maybe some artificial intelligence acceleration chips on that board, if you can buy it from stock, which would boost your performance. If you're not, you would have not the biggest performance, but this would give you a total cost of ownership which would be the lowest in this comparison of the three different systems. The second system I was talking about was the PC-based system, which is quite easy to use. You can take a camera, connect it via USB 3. It will be shown directly in the Pylon SDK, and it's really easy to use, easy to set up. You can take components directly off the shelf. You don't have to do an own board design. You just buy a GPU or maybe a couple of more GPUs for this system, but this will lead to a higher total cost of ownership, or the highest total cost of ownership, to get a performance in the mid-range of these three systems. With the frame grabber based system, which I was talking about at the last, you have a boxed camera with the high resolution chip, because you are able to get a whole amount of data, or a big amount of data, through the, for in this example, CXP12, Coax Express 12 interface. For this, you need the PC with the frame grabber, and so we as Basler can ensure we can provide you with our new Boost series. That's the name of this boxed camera. Together with the frame grabber from Silicon Software, we can ensure you that this is more or less as easy to set up with the plug and play setup as it would be in a PC-based world. This wouldn't be the case if you use a different frame grabber with a different CXP12 camera. It wouldn't be that easy. That's why I only made 2 plus in blue. If you use the Basler setup, we can ensure you that it would be as easy as the PC system. This would give you the highest performance. As we saw in the image, it's 7.3 times higher than if you use a standard GPU for your system. And this would lead to, I would say, not the cheapest total cost of ownership, but in total for the performance you get, it's in the mid-range of the total costs of ownership. So to sum that up, deep learning offers the possibility to automate processes that couldn't have been automated in the past, but you need to make sure you choose the right vision system for your deep learning, and this highly depends on the image throughput. So which kind of camera you want to take, and the inference processing unit, as well as the considerations of robustness and price performance. As I said, I would expect the frame grabber based system as the most robust system, and the embedded system on the other side, the best price performance ratio. But you need to see how fast you want to go, what kind of resolution you want to take, how big your inference would be. If you want to use a Google Net with a whole bunch of layers, it would be a good idea to use it on an FPGA. If you have, as I showed in the demo, a small convolutional neural network, you are able to perform this with an embedded based system. And as the last point, Basler supports you in choosing the right vision systems. Of course, we are, as I said, we have different branches in different countries, and where we don't have a branch, there's always a distributor in each and every country who is keen to help you choosing the right camera. And if you need special expertise in this embedded or FPGA-based field, we are glad to consult you by choosing the right embedded or FPGA system. So thank you very much for your attention. I hope that I made it in time. I think we are good in time. So we have 10 minutes left for a Q&A session. And if you want to get back to me directly, these are my contact details, and I would be happy to answer all of your questions if we don't have time to do this now.
Well, thank you very much, Felix, for an excellent presentation. And attendees, if you have questions, Now is the time to enter them in the question box, and also please do make note of Felix's contact information so you can contact him after the webinar if you have any additional questions. So we'll begin here, Felix, with our first question, which came in around slide 22. What is the footprint of the embedded processing board?
So I will try to jump back on slide 22.
It came in around slide 22, yes.
Okay, but we are talking about this embedded board, I think you said. So I would say this is an outline of 10 by around 12 millimeters, but this is the evaluation board itself. So you can go much smaller in size if you do a custom design. And there are abilities to shrink that down, because here are all the breakouts. You see this USB 3, GigE, HDMI, a slot for an SD card. If you don't need this, you can get rid of this in your own custom design, so you can shrink that down by far, I would say.
Thank you. How about connection with MATLAB or Python? Can we send image to there in real time?
Yeah, that's possible. So if you have a look at the baslerweb.com homepage and then our software section, there's the ability to download PyPylon, it's called. And there you have the ability to run it with Python, and as well in MATLAB, there's the ability to choose Basler cameras. I think for the USB and the GigE cameras, I'm sure. For the MIPI modules, I need to check.
Okay, thank you. Is Pylon 6 available for Linux?
Pylon 6, I think, is not now ready for Linux, but will be in a short time frame available for Linux.
Okay, thank you. Which cameras for embedded applications are included in the Basler portfolio?
We have different cameras included in the Basler portfolio. So this is the Dart series. This is the most common for the usage with the embedded boards, but there's also the ability to use this kind of ACE cameras connected via USB 3 to embedded boards like the Jetson TX2 from NVIDIA or this NXP IMX8 board. And we have this from, I think, 1.3 megapixels up to 13 megapixels in global shutter and rolling shutter and monocolor and color as bare board with an S-mount lens, with a CS mount lens. So there are a lot of different options for your system. And yeah, as I said, just get in contact with us so that we can choose with you the best camera for your system.
Thank you. As Basler bought the Frame Grabber company, do you plan to directly integrate the AI FPGA technology into your Boost cameras?
From my perspective, but I'm not the product manager for this product, but I think not at the moment. It's not planned. I think we are more flexible with the setup where we can have the camera not connected or the frame grabber itself not directly in the camera.
Okay, thank you. What makes your medical cameras different than the other cameras?
Good question. At first, the most obvious point you see directly is the color, but as you can see, they look pretty much the same. So this is why our MedAce is based on the factory automation camera, or the older factory automation camera, and we put on top firmware features, which are low light imaging abilities, perfect color, brilliant image feature set, and we will launch a new feature set beginning of next year, which gives you, to give you a brief insight, there will be a dust protection within these cameras. And we produce them on a different production line directly in Ahrensburg in the headquarters, which brings along the ISO 13485 certification. So for these cameras, we can provide you with product change notification, traceability of components inside the camera, and yeah, that's more or less the most prominent parts which differ from the black version.
Okay, thank you. Do you have any camera working in the NIR range between 1200 nm to 14 nanometer?
We have
14.
special 1400, 1200 to 1400. So we have no dedicated NIR cameras itself. We have ones in the mono field which don't have a filter. So this is the red thing you can see here is the IR cut filter. So the color versions won't work in the NIR field, but we have special cameras, maybe without a cover glass, which have some kind of spectral response in the NIR field. But this is, we should discuss this in detail, I think.
Okay, just to let attendees know, Felix will be getting copies of all of your questions along with your contact information. Next question here. Which pre-processing can be outsourced to the camera?
As I said, the debugging we can outsource to the camera. We can do the sharpness enhancement, and this depends a little bit on the camera family you choose. The ACE family has a bigger FPGA than the Dart series because this is only a single board camera. And with the ACE camera, you have a little bit more abilities, but these are, I think, the pre-processing steps which can be outsourced. You can have a region of interest, multiple region of interest. If you say, okay, I want to look at this corner at the image and this and this and this, you can do a multiple ROI. You can debugger the image 3x3 up to 5x5. Yeah, that's the points where I would say that's the pre-processing you can outsource.
Okay, thank you. Is it possible to buy a system with a finished inference from Basler?
With a finished inference, yeah, there are two possibilities. So we provide this for this frame grabber based stuff. There are two abilities. One is trained and ready inference directly running on the FPGA, but the customer needs to provide us with these images and the labeled images to train the network. We will set up, or the Silicon Software guys will set up the topology of the system and will train the network and then deploy the inference to the FPGA of the frame grabber. And the other possibility is that you come around with a trained inference and only want to put it on the FPGA system. That's also the second case we can provide you with.
Okay, thank you. We're going to take two more questions here, and then we'll close the webinar. And first of those is, which tool will be needed to reach the camera's FPGA? Pylon 6?
To reach the camera's FPGA. So the FPGA in the camera is kind of the brain of the camera, let's say like that. And we put all of our firmware inside this FPGA. And yes, you can directly address this from the Pylon 6 or, for example, the Pylon Viewer, which gives you the ability to grab an image, and you can influence each and every part of the firmware features, so set the exposure time, set the gain, and all of that stuff directly from Pylon. You can do this from the Pylon Viewer, or if you want, you can address this from your code directly. So from my perspective, it's the easiest way. If you don't, or you didn't work before with the Pylon Viewer, open the Pylon Viewer, grab an image, and then there's a feature explanation available in this viewer, and this gives you as well some code samples. You can directly address this feature from your code directly in the API. So this is how you address the features in the FPGA. Yes.
Okay, thank you. And here's our last question. And attendees, please do continue to insert your questions into the question box, and we will make sure that Felix receives them. Last question here. Deep learning requires huge amounts of training data. Does Basler provide help with the labeling of data?
No, not at the moment. So this is not our field of business, I think, because this, as I showed you at the beginning, there's a whole variety of possible applications for this stuff. And no, we will make use, or we give you the ability to consult you how much images you would need to train an inference for the FPGA, but we won't do the labeling.
Okay, thank you. Thank you very much, Felix, for an excellent webinar. And at this time, I'm going to close the webinar. A recording of this webinar will be available shortly. All registrants will receive a link to the recording tomorrow in a follow-up note. If you have any further questions, any questions at all, please do not hesitate to contact Felix or myself, the moderator, and I will forward the question on to him. I would like to thank Basler AG, our presenter, Mr. Felix Chemnitz, and all of you for participating in today's webinar on Vision Systems for Deep Learning, presented by Basler AG and hosted by Photonics Media. Thank you.